Welcome to the Laborers Union, local number 731 here in New York City. Very happy to have you. I understand we have roughly 60 architects and engineers online watching this on Zoom. Thank you very much for attending today. We are here today to provide a presentation on the innovation of seawall stabilization and preservation through permeation processes, which are non-destructive and environmentally friendly. That is really our focus. So I'm very pleased to announce today that the Seawall Repair Network consists of certified and trained contractors across the nation that are able to achieve these goals. My name is Ken Brawley, and I'm the National Program Manager of the Seawall Repair Network. As you just heard, the Seawall Repair Network is a division of Alchemy-Spetec, which is a leader in geotechnical applications utilizing polyurethanes. And I'm joined by my colleague, Mr. Guillermo Salas, who is the marketing manager of Surtreat Solutions, which is a leader in the field of structural life extension. Our shared goal today is to share with you how our technologies are coming together to form an advanced innovation for the purpose of seawall and marine barrier system stabilization and preservation. And to achieve this, we would like to discuss with you the following topics: the causation of seawall failure, more specifically premature failure, and of course stabilization and preservation utilized in our innovations, and how our permeation processes can be utilized once trained by skilled technicians to achieve these goals. Now, before we get started on all the how we do things and what we do, I would just like to spend a moment on why this is important and why the Seawall Repair Network even exists. In 1976, I was about 8 years of age. My family and I had attended a vacation in Big Thompson Canyon in the Rocky Mountains of Colorado to visit some friends that had just built a home there. And it was at that time, after we left, that the worst flood in the state of Colorado occurred that completely wiped out the Big Thompson Canyon. It was several years after that, my father returned with me to the canyon, and the very first thing that struck me when we drove up through the canyon was that nothing was the same. Everything had changed, including the lot of land that our friends had built their home on. And in the place of that lot of land was a shallow river. And then we proceeded up to the top of the canyon in the Drake, Colorado, which is very close to Estes Park. And if you've ever been there, you know what I mean. It's a beautiful place, just magical. But my father showed me the facility that they had built to prevent a flood like that from ever occurring again. The previous one, as my father had explained, just was not stable. It did not do its job. And I asked my father at the time, why didn't they build an advanced system like this to begin with? And his response was very telling to me at the time. His response was, son, I don't know, they could have. Well, that stuck with me over all the years. The reason it was, my father was a geology professor. And if you knew him, you would know that if you ever asked him any question having to do with any kind of earth science issue, he would be in for a long dissertation. But on that particular occasion, he just said, son, I don't know. Fast forward a couple of years, probably more than just a couple of years, I'm standing on a seawall in Marco Bay with a structural engineer who was representing a homeowners association. And he was explaining to me that all the efforts they had tried, various different cementitious materials to stabilize their seawall, were failing. And it just continued to get worse and worse. And so I was looking at the seawall, and I'm looking down to my left, and I'm looking to my right. I was seeing at that point what I had seen hundreds of times, just endless seawalls that were losing soil, becoming destabilized and incurring structural damage that would eventually cause it to fail if the stabilization was not returned. Also, very importantly, I also saw the various different forms of remediation were not effective. The cementitious grouts, hydraulic cements, 57 stone, these alternatives just were not being successful. Fast forward again a number of years, and I'm helping contractors with their seawall projects from coast to coast, from the Great Lakes down to the Gulf of Mexico, and more or less the exact same thing. But it was New York City that really captured my attention here about 2 months ago when I was here. And in terms of preserving our infrastructure, for probably the most incredible city that I've ever been in. And it was as I began to evaluate Liberty Island, the significance of Ellis Island, and of course, the cultural landmarks of Broadway and the Rockefeller Center, And I began to evaluate the proximity of Wall Street, which is the heart of our financial system, both here nationally and internationally, that I realized that this is really where I wanted to be today, to announce this innovation, the stabilization and preservation of these combined technologies that we know will make a difference for protecting what is most important to us. And besides, if we can stabilize and preserve seawalls here in New York City, we can do it anywhere, right? So start spreading the news. Yeah. Sorry about that. So anyway, how critical is this? Well, we know that over the next 20 years, we have roughly $400 billion being projected to be spent on new seawall construction. And after storms like Sandy, we know that this many years later, roughly a decade later, they're still trying to catch up with the number of seawalls that need to be built. And I would suggest, based on my experience, that there were a lot of seawalls that could have survived that storm, but they were destabilized. They fell prematurely. And that is why it is important that we begin to look at our infrastructure now and preserve what we can and stabilize what we can in order to not overwhelm the marine construction industry as well. Now, as we begin to look at what's taking place in Europe right now, the horrible floods that are taking place all the way from Poland down into Turkey and also in China, when you really dig into the news, you start to see what's taking place. We begin to see that there's the seawalls and the bulkheads, the revetments that are failing. And that is why such extensive damage and loss of life is taking place. So I mentioned here a few moments ago, we're going to cover a few main topics. And the first one is the cause of seawall failure. And I would specify that would be premature failure. A lot of these seawalls are failing when they shouldn't be, and what we can do to prevent that from occurring. As I began to research the Army Corps of Engineers specifications for seawalls a number of years ago, it really dawned on me how important it was for these structures to have a solid mass of soil on the landward side. In other words, it needs that soil. It needs that soil that serves as a backdrop to disperse the hydrostatic pressure from the waterward side through the wall and into the landscape of that compacted soil behind it. But it wasn't designed to have a lot of heavy cementitious materials. They're actually heavier than the soil that's trying to support it. As you can see here in this picture, this is a pretty good example of a 3-year seawall that is already beginning to experience major soil loss. You can see the depressions behind it. One of the things I'm always quick to point out to people is that if you see these kind of depressions that are beginning to form behind the seawall, it is literally the tip of the iceberg. Below that, between the mean water line and the mud line on the waterward side of the seawall, there's a much greater void that is beginning to occur. And that is very problematic. And I'll explain that here in just a few more seconds. In this illustration, we can see from a cross-section exactly what I'm referring to. You can see some depressions on the landward side of the seawall, but below it, on the landward side, you can see the void that has begun to form. Now, at first glance, especially from an engineering standpoint, you would think that the waters would cancel out. But what I'm going to discuss today is how when those voids fill up with water, it doesn't matter if it's high tide or low tide, whatever the case may be, there's several things that are taking place. One, you have a lot of liquefied soil behind the seawall because of its proximity to the seawall. Secondly, when you have a body of water behind the seawall, that all of a sudden receives a high volume of additional water from heavy rains, storm surge, flooding, whatever the case may be. Now all of a sudden you have an exponential volume of hydrostatic pressure on the landward side to include liquefied soil. When the waterward side of the hydrostatic pressure begins to recede and return to the mean water line or low mean water line, all of a sudden now we have this offset of pressure that the seawall was never meant to experience. But it all started with the voids that formed behind the seawall. And this is a really good example of what I'm referring to. This is a top of the seawall cab, as you can see. And the diagonal break occurred because of the buildup of hydrostatic pressure from the landward side of the seawall. When the waterward side pressure receded back to the mean water line, there was enough landward side hydrostatic pressure in the voids behind the seawall that caused a sudden, what engineers typically refer to as the moment of failure, that destroyed the seawall cap. Now, from this other angle of the same seawall, you can see that because the seawall cap failed, it wasn't able to hold the panel seams, the vertical joints together, and they actually started to break apart, as you can see right here. And also very importantly, of note is as this seawall was trying to hold on for dear life, essentially, from the void formations that had formed behind it, there were minor structural damage that was taking place that was allowing water intrusion to start touching the steel reinforcement. So it was a gradual process. And in this particular case, the seawall, which was about 3,000 linear feet and was owned by a municipality, they also had tried all sorts of other types of remediation involving cementitious material, including hydraulic cement and pressure grouting. And at this point, I'm going to let Mr. Gammo discuss the internal injury to the structure itself.
Thank you, Ken. Well, now that we know the external causes of seawall failure, let's take a look at what's happening inside the concrete. Concrete is really, reinforced concrete is a technological wonder. It's been around since the 1850s, and nowadays we can see it in pretty much every structure around us. But like any other material, it fails, it deteriorates, and it's important to know the cause of that failure and deterioration. The main cause of reinforced concrete failure is the corrosion of the actual reinforcement. So what's happening in broad boards, we're going to go in more detail in later on. But what's happening is that the corrosion is forcing, it's laminating the concrete, and the expansive stresses are forcing the concrete in the surface to chip, spall, or crack. So this is not only a problem for the seawalls. If a seawall fails, it's not just the seawall that's failing. That water leach can actually penetrate into structures that are around the seawall. It can go into basements, it can go into boardwalks, boathouses, houses, parking garages, anything that's around, because water looks for the path of least resistance. And it'll usually find it, and it's attracted to other structures that are nearby. So it's not just a problem of the seawall, it's a problem of everything around the seawall and the environment around the seawall. We're seeing this right now in Florida, where corrosion had a catastrophic impact on structure. So it's not just the damage to the seawall, it's the damage that's happening around the seawall.
So at this point, we've discussed a couple premature causation of seawall dynamics. And there's another one at play as well. Again, here a little while ago, I referenced the research into seawalls as specified by the Army Corps of Engineers, but also one of the issues that came up was their lifespan. One of the big questions is, why are seawalls not lasting as long as they should? I had a long discussion one night with a retired member of the Army Corps of Engineers, and he was really adamant that these seawall structures, as specified, should last upwards of 100, and in many cases, 120 years. But we were seeing seawalls failing after 10, 20, 30 years, in some cases a lot sooner than that. And this is one of the reports that the gentleman had supplied to me for the seawall project on Balboa Island. So that really begs the question, is there another factor at play here as well? When the Army Corps of Engineers started to specify seawalls back in the 20s and 30s, one of the primary ingredients of their construction specification for erosion control, prevent the external dynamic that we referred to just a few moments ago, was the application of a very durable filter fabric to prevent void formations from occurring on the landward side of the seawall. In this case, we're really referring to a needle-pinned, unwoven geotextile filter fabric, which in today's standards is extremely expensive. And it wasn't just the material that they were utilizing. They were draping the entire landward side of this material, all the way from the bottom of the seawall cap, all the way down to the toe of the berm or beneath the footing itself. What we are seeing nowadays, and I see this again coast to coast, from the Great Lakes all the way down to the Gulf of Mexico, is instead of draping these structures with that kind of material, they're utilizing typically furring strips, or basically wood strips to tack the material, as you can see, vertically across vertical panel joints. And this is really one of the key items that they're relying on in terms of construction to prevent the void formations from occurring. Right off the bat, there's a couple of problems. One, they're typically not installing this material beneath the seawall itself as it's being installed. Now, that may not be the case for every contractor, but I've seen this time and time again. And another issue is they're no longer using that highly durable needle-pinned and woven geotextile filter fabric in many cases that I have witnessed. And as you can see here, I painted a sample of what they were using on that particular project that was owned by a city in South Florida. They're really using more of a material akin to landscape material, which is a woven type of a plastic. And it just doesn't last long. It breaks down very quick. And in many cases, we're seeing significant void formations in as little as 2 or 3 years with the newly constructed seawall and other waterproof barrier systems. Now, we certainly did not come here to insult anyone today. Construction costs and margins, it's very difficult. And as I mentioned before, that very durable erosion control material is very expensive, very expensive. But the fact of the matter is, there are innovations now that are highly cost effective. And as we begin to move into this, we'll discuss how these innovations can still preserve and stabilize structures. As an example, a seawall, typically in the range of 70 to 80% less than the cost of ripping out and replacing the seawall. This is one of my most favorite examples. This was a city-owned seawall, and the city official, who was a structural engineer, explained to me that over about a 4-year period, they had quite literally tried just about every form of cementitious material, the traditional methodologies for seawall remediation. And he explained to me that it just was not working. And as you were to dig into this picture here, you can see that they tried to reinstall the filter fabric. That did not work. And he explained that they proceeded to put in 57 stone. And then they proceeded to do some hydraulic cement and jet grouting. And you can see the grout column, in this case, right here at the joint, at the corner of the seawall. And he explained to me that this column continued to sink immediately because it was just far heavier than the liquefied soil that was trying to support it. And as it began to sink, about 2.5 feet, it began to fall forward into the seawall structure. And as you can see, the concrete block is starting to pull apart. Right in this area right here. So again, we're not beating up on anybody. People again have been trying to do the very best that they can, but we do believe that there's some better ways of approaching this issue. Here, about 2 months ago, I got a chance to go out to Governor's Island, and beautiful view of Manhattan. This particular section of the seawall actually pointed right towards Manhattan. And as soon as I looked down the long span of the section of the seawall, I could see that it was beginning to overturn. And because of the movement of the structure, the seawall cap was starting to break up apart a little bit. And there was a reaction to it. The picture on the right, just on the other side of that fence, you can see that a trough had been dug and some form of cementitious material had been installed at that section of the seawall. All right, the next key point that we would like to move into is the actual reason we're here today. And that is the innovative method of stabilizing seawall structures and other marine and waterfront barrier systems. Now, to have a meaningful discussion about stabilizing the seawall with advanced technology, we really need to address 3 separate issues. The first one is the material that we recommend and that we have manufactured. The second one is the equipment to effectively install it. And then, of course, the third one would be our patent-pending installation techniques. In this particular picture here, you can see a construction worker installing the material. The material that we're discussing today is a 1-part polyurethane resin that is environmentally friendly. It's safe to be in compacted drinking water, is rated by the National Sanitation Foundation. The material is moisture activated, so that as soon as it begins to encounter any moisture in the soil, it immediately activates this 1-part polyurethane resin. As it activates, it has a 50 times spread and expansion factor, and it immediately begins to permeate into the landward side soil as opposed to displacing the soil. In other words, it doesn't cause soil fracturing, which is one of the major drawbacks of the application of cementitious materials behind a seawall. As the material is permeating into the soil on the landward side, it's filling up any voids. Again, it has a 50 times spread and expansion factor. but it's also bonding to the landward side of the seawall. So effectively, because we replicate this, as we'll discuss here in a few moments, we're effectively bonding the entire structure to the landward side. And what that does is it changes the environment, the soil environment on the landward side from a dynamic environment where soil is able to move, erode, cause void formations, into a static environment. Liquefied soil does move laterally and downward. After we permeate that soil, now that it is static, the load transfers from the lateral load at the time that it's liquefied to a vertical load, because now it is a solid mass. After this presentation is over, there are some samples of the resin that we're talking about. When this material permeates into the soil, it very commonly can develop a compression strength of 2050 psi. So it's rock hard, but unlike cementitious materials, it's about 140 times lighter. So it's actually lighter than the actual soil that's supporting it. Whereas the cementitious material is a lot heavier than the liquefied soil that would support it. And that is why this material does not sink. Again, it's bonded to the landward side of the seawall, it's permeated into the landward side, and it stays right where it needs to be to do the job of preventing void formations and the destabilization of the structure. Now, just as important in many ways as the material itself is actually getting the material to where it needs to be. And we have customized a high-powered gas over hydraulic piston machine that has a hydraulic ram on it. And what's really unique about this machine is on the pump side, it's able to produce upwards of 3,300 psi in order to keep the material moving. However, at the point of application, where we actually inject the material into the landward side of the seawall, it's only coming out at roughly 100 to 200 psi. And that is how we're able to prevent soil fracturing and soil displacement. Any soil displacement behind a seawall, especially down near the toe of the berm, is likely to cause lateral stress against that structure. And with our equipment and the material itself, we're able to prevent that from occurring. Another great thing about this equipment is it's light equipment, and it gets the job done. It can fit onto the back of a flatbed pickup truck, and it has two hose drills that can extend out over 1,000 linear feet, and is able to produce the necessary pressure to get the material at the point of injection. The reason that is really important, again, we talked about void formations behind seawall structures. Taking heavy equipment, for instance, undercast piling machines, that type of thing that are very heavy, it's very dangerous to do that behind a seawall. With this equipment, we can simply extend the hose drills again out to over 1,000 linear feet, and the crews are able to get the work done without the unnecessary danger of equipment falling into voids behind the seawall. Now, the third item we need to discuss with the advanced and innovative approach towards stabilizing seawall structures is our patent-pending installation technique. And this will require a little bit of visualization on your part. I'm going to do my best to describe it to you. In order to effectively install this material, the 1-part polyurethane resin, we utilize injection pods that are typically a 1/2 inch diameter, galvanized steel tubing. And the crews are typically able to drive down these injection tubes directly behind the seawall itself in regular intervals, depending on how the seawall structure is set up. It's typically about 5 feet in span on center. And we replicate that from one end of the seawall to the end of the project site that we're working on. Once we have accomplished that, we simply utilize a process called upward staging. We get the rods driven down either manually or mechanically to a depth equivalent of the footing of the seawall or to the toe of the berm. So once we begin to inject the material, we're stabilizing the soil at the very base of the structure itself. As we continue to inject this material, we utilize the process of upward staging, and we complete the installation at that particular injection point at the bottom of the seawall cap. There is no exposed polyurethane resin above the topsoil layer. Once we have replicated this from one end of the seawall to the very next, we have completely permeated the landward side soil of the seawall structure. we have completely permeated the seawall on the landward side and changed it from a dynamic environment to a static environment with stabilized soil, which is now stabilizing the structure itself. We still have a problem. We have to get rid of the hydrostatic pressure. Now, via our design, specifically the director of our geotechnical division, Mr. Cole Hollander, he developed a really neat system. Again, that's in a patent pending status at this point. And this is where I really need your help with visualizing this. Now, all the work at this point has been done on the landward side. In order to alleviate and dewater the landward side hydrostatic pressure, the crew members use a hydraulic core drill, typically about 3 inches in diameter, and they create dewatering channels in between the injection points. Hopefully that makes sense. So from the waterward side, utilizing a hydraulic core drill bit, where this permeated soil is actually thinner, we create a dewatering channel through the seawall, through the permeated soil, and into the fresh soil. Now, another way of looking at this from that bird's eye view, utilizing the injection rods, the permeated soil is naturally going to be thickened at the injection point because of the interaction with the soil on the landward side. The dewatering channels are being created in between the injection points where the permeated soil is actually thinner. If you think of a roller coaster that's consistent from one end of the seawall to the next, that's essentially how we're able to optimize the dewatering of the hydrostatic pressure, because when water always takes a path of least resistance or piles up on the landward side of the seawall, because the material that we injected is hydrophobic and will not allow water to pass through it, the thickened masses of permeated soil that we have created with our installation process deviates the water towards the center of the injection points, which is where exactly we created our dewatering channels. Now, the next step is to make sure we don't have any more erosion. So what we do is we install a panel filter, and this is just a really good example of a conical panel filter, and we install this on the face of the seawall itself. Now, this allows water to pass through, but it will not allow soil to pass through. It's actually a patent that's been in existence for about 30 years, and it is highly effective and time tested. And at that point, we really have achieved a lot of things between the material, the equipment, and the actual installation technique. We have stabilized the structure. We have created a very consistent and highly effective dewatering mechanism to dewater that hydrostatic pressure that we know causes destabilization and movement of seawalls. And that is how we're able to achieve our goals for stabilization. Now, we are not here today to claim that the polyurethane resin is a cure-all for stabilization for pre-existing seawalls. Seawalls are equipped at the time of installation, typically, according to the specifications, with an anchoring system called a dead man anchor. My wife seems to like that name for some reason. I'm not really quite sure. Dead man anchor, but that's some ideas for you maybe. But anyway, as you can see here, dead man anchor is typically a block of concrete that leads into the seawall cap most of the times with a tie rod, which is a steel rebar. And it serves a very critical purpose of preventing failure. A lot of times dead man anchors fail because of hydrostatic pressure, but also in relationship to its position, typically 10 to 20 feet behind the seawall, it needs that soil mass between its location and the seawall structure itself. If the void formations have occurred, obviously the dead man anchor can be pulled forward. That's a lot of times where we see seawalls begin to fail. This is another example of an illustration that provides exactly a reference to what I'm referring to right now. In the top picture, you can see a broken tie rod and a dynamic referred to as overturning. That is where the seawall begins to fall forward and the seawall cap towards the water. And then, of course, on the bottom, you can see an example of what is referred to as kick out. And when a seawall kicks out, it's typically a result of undermining of the structure altogether. And enough hydrostatic pressure has built up once again in the void formations on the landward side of the seawall. And that pressure, a lot of times after a heavy rain, forces the bottom of the seawall to move forward and causes quite a bit of polyurethane resin for stabilization purposes in relationship to our installation technique is highly effective. If a structure has indications at the time of evaluation, especially as advised by an engineer, we will still permeate that seawall. We will still create the dewatering channels. However, we will still recommend the installation of helical tiebacks. And helical tiebacks have been in use for over 100 years. They're time tested, they work. Typically, by using torque and a hydraulic dry fed, we're able to drive a steel piling with the helical plate that is attached to the very first pile. And when we generate, according to Shoggy's load bearing capacity principle, about 2,500 psi on a dry fed, we know that we have locked in or tied in that helical plate into load bearing strata. And then we simply use an all-thread bolt to connect it to a seawall plate on the face of the seawall on the waterward side. And at that point, we know that that seawall has been retrofitted with a highly effective anchoring system. So at this point, we have discussed with you an innovation using polyurethane resin that is environmentally friendly for the stabilization of seawalls and other waterfront barrier systems. And just a few case studies where we have used this exact same material and process. One of them involves the Marathon oil terminal in the Gulf of Mexico that involved about 400 linear feet of seawall. And the reason I thought this one was very relevant is anybody that's been watching the Gulf of Mexico for a number of years now, especially the last 2 or 3, knows that there's been a lot of tropical storm and hurricane activity. And there has been no reported failures of the work that we accomplished on that particular seawall. These projects work for stabilization purposes. Another thing that I just want to point out really quickly is that these same materials, 1 part polyurethane resins that is produced by Alchemy-Spetec, have been used right here in New York City for grout work, for grout curtains in the New York City schools, and also the water treatment plant here. But there's one case study that I just wanted to really highlight today for stabilization with this innovation. And that is the very recently completed project in our nation's capital at the DC water plant. The capital's architects and engineers saw fit to build a large structure around DC water treatment. And its proximity to the Potomac River made that decision very critical because they were very concerned about major flooding and the devastation that could occur should that facility be flooded out. So they built a huge seawall basically around the plant on the banks of the Potomac River, but they had some problems and weren't able to get the sheet pilings down deep enough. Well, long story short, for about 3 weeks, there were some very stringent testing that occurred. LJS Waterproofing, Mary Grubbs, responded, and it was determined by the engineers and the city planners that the same material, the same equipment, and the same process, installation techniques that we discussed over the last few minutes were utilized for this project. And I'm very happy to report that it was a tremendous success. At this point, I'm going to turn it back over to Guillermo. He's going to discuss the preservation of seawalls.
Thank you, Ken. So now that we know that we can stabilize the seawall, let's talk about actually preserving the structure. So let's go ahead. So first, we need to understand what exactly is causing the seawall to deteriorate. Concrete, reinforced concrete, when it's new, has a high pH, and that makes it a very alkaline environment, which means that that rust is not going to be able to generate as long as it's alkaline, and there's a passivating layer on the rebar. As time goes by, concrete will start to crack, will start to shrink, will start to expand, and through those cracks and through those gel pores, water, acids, air, chlorides, chemicals are going to start penetrating the concrete and causing that pH, that high pH, to start lowering. As the pH lowers, that alkaline environment changes to acidic, and that's going to start eroding the passivating film on the rebar. When that passivating film on the rebar is eroded, corrosion is going to start to set place. Eventually, when enough corrosion, enough rust is generated, it will have expansive stresses on the structure, on the concrete, which will then delaminate, expand, crack, spall and generate that. You've probably seen it a million times in the structures where there's a big spall, rusted rebar. That is exactly what happened. And that's all through chemistry. That happened through chemistry. So we got to understand that if we don't fix the underlying condition of the concrete, that low pH environment, this is just going to happen again. The corrosion is going to keep expanding through the rebar. New hotspots are going to surface, and the process is just going to repeat and repeat no matter how many times you patch. So we need to understand how to fix this through chemistry. We need to understand how to cure the concrete. What we need to do is whatever corrosion that's already in the rebar, we need to turn it into an inert shell so that that corrosion doesn't keep expanding through the rebar. Once that's done, we need to elevate the pH of the concrete because we need it again to be in that passivating state where corrosion is not going to be able to set in another part of the rebar. We need to make the concrete stronger, so we need that free calcium that's out there to bind together and make a new concrete and a new structure, make new concrete out of the free calcium that's free. We need to increase the compressive strength so that the concrete is harder. We also need to close those pores and seal that porosity so that no new contaminants can come in and damage again the pH, lowering it and repeating the cycle. So the best way to do this is through chemistry. We got to cure the concrete through chemistry. And it is through chemistry that migratory corrosion inhibitors were developed. Now let's talk about, we'll show some case studies of how these migratory corrosions were developed and the results. We're going to talk about, it's been tested in the Pennsylvania Turnpike by NASA, by the Department of Defense, by private companies like Boeing, and it's been used in buildings and structures in New York like the LaGuardia Airport. So I'm going to talk today about the NASA projects and the Cadena Department of Defense project. So in 1986, and here are the results for reference while I speak about this. But in 1986, NASA realized that they had a big problem. The structures, their launch pad, were going to deteriorate faster than they originally thought. The reason for this was that the rocket boosters, when they were ignited, they launched a lot of chlorides and a lot of contaminants into the concrete. Then, to aggravate the situation, to cool down those launch pads, water was being thrown down, driving all those contaminants into the concrete, into the rebar, causing that deterioration to occur faster. So they set out a study to determine what's the best way to treat this and fix this problem, because at that time, the solutions that were available were very expensive. You need a lot of maintenance and a lot of monitoring. So through a study to test a vapor phase corrosion inhibitors, they determined that the surface had to be treated. So a migratory corrosion inhibitor system was developed that showed amazing results in reducing the corrosion rate, reducing the porosity of the concrete, and increasing the compressive strength. So all the things that NASA was looking for, they find it in this migratory corrosion inhibitor. Now, fast forward a few years, the Department of Defense found in a study they did on corrosion on the military bases the same issue. They found that corrosion was affecting their budget and their readiness. So through studies that they made, they decided that there was 2 bridges that was a perfect demonstration setting to test this new migratory corrosion inhibitor system that NASA used. So these culverts, these 2 bridges were a spillway, and they were constantly flooded in water. So they set out in a 10-year study to determine what was the best system to address this corrosion issue. And the result was that a migratory corrosion inhibitor system that included that migratory corrosion inhibitor, the vapor phase corrosion inhibitor to treat the hotspots, the corrosion hotspots, and the silane siloxane sealer was the best system that they needed for the corrosion issues. So after 10 years, they came back, they tested the results, and their findings was that same concrete structure was 70 to 80% there was a 70 to 80% reduction in the corrosion rate after 10 years. So after the 10-year study, they determined that this three-part system was the best solution for the corrosion issue that was deteriorating their infrastructure. Now, thanks to this, the military, the Department of Defense decided to implement this corrosion system into their Department of Defense Unified Facilities Guide specification. And to this day, this is the method they use to treat corrosion from the surface through a surface applied system. Now, so far we've discussed the stabilization of seawalls through permeation. Now we know about the preservation of seawalls through permeation, the concrete seawalls. But in this area, most of the seawalls are steel. So what is the technology that we can use to treat that corrosion in actual steel? Well, the same technology, the same migratory corrosion inhibitor technology was then applied to treat bare steel, bare metal. So the same migrating through the rust, through the layer, all the way to the steel, but now it can be used to treat just metal structures. And it doesn't need to be concrete. It's the same migratory corrosion inhibitor that's added into a military grade steel primer. And this is just an example of that steel primer that's used on a drum barrel. Half of it was treated here with that steel primer and the other half wasn't. Then this was left to the elements for 3 years. Now, the important part here is that because it's a migratory system, it doesn't require the same amount of surface scrap that a traditional system requires. I'll talk here. So this was a case study that was done in Houston, Texas, on two steel bridge elements. The first one had to be treated regular surface scrap, containment, all the rust, all the special processes that need to be taken care of, environmental processes. And then after a year, we notice here that the corrosion is still appearing because it's not migrating all the way to the steel layer. If you can't surface prep a certain part, then there's going to be corrosion coming back into that portion of the element. Now, the other steel primer, the migratory corrosion inhibitor, goes into those recessed areas and treats the whole, because it migrates through the rust into the white steel. You can see that there's no corrosion spots in there, and it's basically protected against those elements and the corrosion. So we have three technologies that help us protect and preserve and stabilize seawalls. We have a seawall stabilization technology. We have a penetrating technology for concrete seawalls, and now we also have a penetrating technology for steel seawalls. Now, how do we bring this together through the seawall repair network? Well, through the seawall repair network, we focus on those 5 E's. We want to make sure that every solution that we give you meet those 5 E's. So we want to make sure that it's enduring, that it's a permanent solution, that you're not going to have to go back, fix it again. It's not a band-aid. It's a solution. It's a cure. We want to make sure that it's effective, that it treats the actual underlying condition. We want to make sure that it's efficient. Like Ken mentioned, this can be even 70 to 80% faster than traditional methods of repair, meaning that you will have more time to do more seawalls, more work, instead of focusing all your energy in one project or a small amount of projects. It's environmental, SNSF approved. It's water-based technology that can be used in potable water, in areas with access to potable water. It's also helping preserve that infrastructure. That means that because it's helping preserve the infrastructure, there's no need for new concrete, for new structures. And concrete is it's the third largest polluter in the world right now. If it was a country, it would be the third most polluting country in the world. It's actually, concrete production is accountable for 8% of total CO2 emissions. And it's economical, like Ken said, 70 to 80% cheaper than traditional methods of repair, which drives back to the point. You can do more projects, you can do more with less, you can stretch your resources better. So we're looking for those 5 E's whenever we mix the technology into the seawall repair network. And results matter. We want this to be, we want our customers to not talk to us again. We want them to get a seawall repair and that's it, on to the next project. We want those to be permanent technologies. And it's green, like I mentioned, it's NSF approved, it's water-based, it's good for the environment, and obviously less concrete, less pollution.
Really, in the presentation, I gave you an example in my life. There was an opportunity for myself to ask my father why something wasn't done. The use of single component polyurethane resin, perhaps not as advanced as what we're discussing today, has been successfully utilized with seawall work for remediation for over 30 years. There is an actual time-tested history for this. And of course, as Guillermo has mentioned, the preservation materials have been utilized and tested and passed the Army Corps of Engineers testing standards now also for 30 years. So the next logical question that I would ask, I guess from the standpoint of a child, is why? Why are we not utilizing everything that we've talked about today for new seawall construction? The technology is there. It's just time to actually put it to use. Initial analysis, I believe, shows that if we were to incorporate the stabilization and preservation materials and techniques through permeation, we'd only add a cost of roughly 45% of the overall cost of new seawall construction that is actually taking place today. And I think that's a question that we would like to talk to our engineers here in the Northeast and across the globe, about how we can begin to work together to put these innovations into place. In 1962, a renowned sociologist by the name of Ian Robinson wrote a book called The Fusions of Innovations. And he basically broke us down into 5 categories, which haven't really been disputed, but basically we all kind of fall into a category according to this theory. About 2 or 3% of us are the innovators. I like to think of our engineers and architects as people who like to come up with creative ideas. We have early adopters, the people that see the promise, still a smaller segment of the population. And then we have our early majority, a late majority, and just messed up. Well, at any rate, I messed up the slideshow. I apologize for that. But we have our laggards, and these are just skeptical people that just will not come on board with what we are talking about doing because they resist change. But we are now, in fact, at the point where the innovations that Guillermo and I have been discussing today are actually taking place. One of our recently completed projects, I think it's I did the wrong button again. I'm gonna have to get used to using this. This is a very recent project in Lake Pontchartrain in Louisiana. And what you're seeing there is the soil stabilization, preservation of a major waterfront barrier system. Anybody that remembers, of course, Hurricane Katrina and the devastation that it incurred in Louisiana, and the subsequent work with the Army Corps of Engineers understands the incredible amount of work that was done there. But everything that we were talking about today has been done just recently. And so these are the innovations that we want to bring mainstream for the improvement of our resilient shoreline communities. So as we wrap up today, there's just really 4 things that we would like for you to remember as we move forward. Again, as Guillermo stated, we're looking for permanent solutions. I think that days, especially when it involves infrastructure and everything that is at stake, we don't just put into effect temporary solutions, things that we know don't work long term and perhaps don't really stand up to storms, storm surges, and hurricanes, and these kind of things. We know that what we're talking about works. It has stood both the test of time and also natural disasters. Everything that we've also spoken about today is applicable not just to seawalls, but a wide variety of infrastructure, for instance, dams, tunnels, bridges, and in terms of keeping laborers working. We're at the local 731 union today. There's a lot of work to be done with these technologies and innovations that we've discussed today. again, I can't stress enough, in the era of environmentally conscious materials that are being utilized, everything that we've discussed today is environmentally friendly. And when we consider the alternatives, for instance, cementitious materials for this kind of work, and consider what's actually causing the carbon footprint, automobiles, obviously, they get the number one ding for causing a carbon footprint. The number two is the mining of cementitious aggregates for making concrete. So it's really time that we begin to utilize more environmentally friendly, conscious solutions that are not dangerous for our environment as a whole. All right, this wraps up our presentation at this point. I know that there's a lot of people that have stayed with us on Zoom. I greatly appreciate your attendance. We want to get to know you. Please call us at 470-204-2368 or email us at info@seawallrepairnetwork.com and give us your contact information. We would like to partner with you and begin to discuss how we can form a working relationship. For everybody here, please stick around. We have some samples and some handouts for you. And there's also a bag that has a flash drive on it with a lot of the specifications and tech data sheets for the materials that we discussed today. And at this point, I'd like to turn it over for Mary. And Mary is the one that brought us all together. Here about 3 months ago, I took a road trip with LJS Waterproofing, evaluating seawalls all the way from Maryland up to Maine and across to Pittsburgh. And it was Mary Grubbs from LJS Waterproofing that introduced me to a chemist by the name of Tony Fiasco in Pittsburgh. And it was that invitation that led to this entire event coming together today, all the relationships that have been built since then. So thank you, Mary.